Hello students. On the last round we had discussed harmonic oscillator for diatomic molecule. As we already discussed, then this oscillator is not sufficient to explain all behavior of diatomic molecules. So this model has been updated, and today the topic of discussion is anharmonic oscillator and Morse equation. Morse modified the harmonic oscillator concept and give a new concept. We will discuss this concept in this lecture. In this lecture, first we will discuss why we need anharmonic behavior. Why anharmonic behavior exists in vibration of diatomic molecules. Then we will study Morse curve suggested by PM Morse. How changes in energy takes place here. In the last turn we had discussed then the energy levels difference are same, constant, but what changes will take place here we will discuss, and finally we will discuss hot bands, interesting concept from vibration models. We all are convinced with the fact that the real molecule do not obey the laws of simple harmonic motion. But in the last turn, as we have already discussed, in place of studying the detailed Hamiltonian behavior and other behavior of the diatomic molecule, it is easy to study energy eigenvalues and possible curves. And Hooke's law based harmonic oscillator is the simplest way to learn. But the real bonds, the bonds between the atoms, we know this that the classic, although these are we always say these are elastic, but these are not elastic at all limits. They are not so homogeneous as to obey Hooke's law always. For a smaller values, they may obey Hooke's law. But for larger amplitude, suppose we increase the magnitude from 10%, more than 10% to length of bond, then this will become more complicated and they gives complicated behavior than the normal behavior. We also know that if we apply very high energy, then they not only become inelastic but may also break in atoms. If they break in atoms, then definitely harmonic oscillator cannot work there. The real shape of typical energy curve so might be different to ideal simple parabolic spectra. What changes we should suggest, we will discuss in later slides. PM Morse suggested a different curve, and on the basis of this details, the potential that he suggested, also called Morse potential. According to this potential, interaction model for potential energy is different than harmonic oscillator. He suggested that in this model that the restoring force is no longer proportional to displacement. Restoring force means the force whenever we either compress or extend our bonds, then the restoring force exists. these forces are always against our action. If we are compressing, the forces want to open this. If we are extending, they want to compress this. So these forces are there, but normally these forces are proportional to displacement. It's called as per Hooke's law. But in our case, what Moore suggested that these may not be proportional to displacement. See this curve and try to remember the old curve. The old curve similar to dashed lines. Harmonic oscillator, which is symmetric to both from equilibrium position. But Moore suggested different curve. This is not symmetric. I think you are maybe aware of this. On the vertical line, we assume one atom, and the second atom is moving towards each other, away from each other. This suggested that in this extension and compression, they don't follow Hooke's law, and so the behavior is different on the higher section. This section, see this area, different behavior. This is not proportional. So this behavior is given by Moore's law, Moore's equation. We should also on the y-axis I am plotting energy, which is continuously extending, and on the x-axis I am discussing interatomic distances. Morse had given empirical expression. That expression is called Morse function. I think all of you are aware with this word empirical. Empirical means based on observations. There is no back of this from this not he is not obtained from anywhere. He has thought on this and given on the basis of observations. That is called empirical. And according to Morse function to incorporate this curve should be this. E is equal to d equilibrium 1 minus exponential of A bracket R equilibrium minus R and whole square. A is called constant for particular molecule. So for molecule this value is constant, and D equilibrium is called dissociation energy. He suggested this curve for real molecules. If we use this energy in Schrödinger equation, then allowed vibrational energy level is found to be E nu is equal to nu plus half omega E minus nu plus half square omega E psi E centimeter inverse, where the value of nu is 1, 2 and so on. Here omega is oscillation frequency and psi E is anharmonicity constant. See this here. The second term arises due to anharmonicity, arises due to inelastic behavior of your atoms, and this is suggested by Moore's function. Moore suggested then your harmonic behavior is not sufficient to explain this behavior, so you have to add something. If you have to add something and use that energy in Schrödinger equation, you will get this answer. This band and psi E gives you idea of stretching of bands. And this band stretching vibration is always small but positive, and it may have value 0.01. More closely together with increasing energy. This is also shown in figure. Now see this figure and try to remember old figure. Dissociation energy is dEq is given. After this, your molecule will dissociate. Molecule will not be molecule, it will become atom. So you cannot apply this energy for molecules. D0 is the energy. One interesting thing you can see here, that the energy level as you move, or the higher energy level, the energy level difference is decreasing. The levels become closer as you move away. And the graph is also not symmetric as at left and right. We should also remember that these values we calculated, they are still approximate, because if you want to go get precise expression, then cubic, quarter or higher term should be added with nu plus half. Here we have added only square term. If you add another terms for nu plus half square, cube, nu plus half 4 and so on, then this should be with ye, ze in place of psi. And this value of these component is rapidly diminishing magnitude. These terms are important for large values of nu. But here we are ignoring all the terms. We are ignoring y and z. Now we can write our equation energy as omega E 1 minus I nu plus half square. 1 plus I nu plus half and nu plus half we have taken common, or omega oscillations can be done as omega E 1 minus x plus half. So we can say the anharmonic oscillator behave like a harmonic oscillator which increases steadily with increasing nu. We can assume that hypothetical energy at nu is equal to minus half. You just put nu is equal to minus half in our equation. So nu oscillation will be equal to omega oscillation will be equal to omega E. This is called hypothetical equation oscillations. This is called hypothetical equilibrium oscillations frequency of an anharmonic system. But again, it is hypothetical because nu is equal to minus half is not possible. Frequency of an anharmonic system for real state generally having this form. Omega is equal to omega E 1 minus half xi E, or E can also be done as 1 upon 2 omega E 1 minus half psi. Here see that the 0 point energy is slightly differ from harmonic oscillator. Slightly differ. You can see the things. We have calculated 0 point energy using harmonic oscillator, and in real practice for many atoms that 0 point energies cannot be explained. By using harmonic oscillator we have explained, yes, if your material is not giving truly harmonic behavior, then this will be the 0 point energy. Now our job is again to apply selection rules. Here the selection rules are del nu the change in energy shall be plus minus 1, plus minus 2, plus minus 3. Same as used above with additional possibility of longer jumps. Only in the past case we have added only plus minus 1. Now we have used two more, plus minus 2 and plus minus 3. We can calculate the following things. Suppose we move from nu is equal to 0 to nu is equal to 1. It means del nu is equal to plus minus 1. If we do this, then you can calculate change in energy. Del E, del 1 to del 0. Try to calculate this using the values. We will get the answer omega is equal to 1 minus 2xe. Here I have shown this answer. Now, as we know, in our case, we can also find out nu is equal to 2. So if we do this, second will be the answer. Two nu e. And we can also calculate for 3. This will be the answer. 3 nu e. And these are symmetric. 1, then 2, then 3, and then so on. But we must check this also. Intensity is high, intensity is small, and intensity is negligible. As so, for del is equal to plus minus nu is equal to plus minus 1, the intensity is high. But for 2 and 3, the intensity is low and very low. These lines are close to omega A2, omega A3, omega A called fundamental absorptions. First and second overtone respectively. So in some materials, we have some additional peaks, and these peaks can be explained using Moore's plot. For example, if we take the values of HCl gives 3 peaks, one first at 2886, second at 5668, and third at 8347. Interesting, 1E, 2E, and 3. Now, these peaks can be used to calculate various equilibrium values, omega A, and other constants. We can calculate. I also want to add one interesting fact here. In all studies, we ignored transition from nu is equal to 1 to higher studies. But this cannot be ignored in high temperature studies or at lower temperature, such as weak absorptions. In this case, when such type of absorption occurs, called hot bands. Hot band means this occurs only normally on higher temperature or weak frequency. These conditions of occurrence is there. Nature may be confirmed by raising the temperature of samples when too hot band increase in intensity. So we have finished very important topic of this unit. Again, I request you to go to the book I have already sent you online and see the discussions. Thank you and take care.